In this lecture, we're going to cover section 1.5, which is quadratic equations. So on the first slide, we have the definition of a quadratic equation, and you might remember this from algebra from, pre this course. A quadratic equation in X is an equation that could be written in the standard form ax squared plus bx plus c is equal to 0. So that's the standard form of a quadratic equation. A, B, and C are real numbers, and A can't be equal to 0. And the reason for that is if A was equal to 0, then the x squared term would be zeroed out, right? And we'd just be left with a linear equation. And we could also call a quadratic equation a second degree polynomial equation because its highest power is 2. So we're going to look at solving quadratic equations. There's a few different approaches that we could take to solve a quadratic equation. I like to approach each quadratic equation when I'm going to solve them by thinking about, okay, once I have it in the standard form, am I able to use factoring to help me solve? Because I think that's quicker sometimes than using the quadratic formula, but not every polynomial is factorable, right? But before we even go back to factoring, and we did go over factoring in earlier videos, the reason that factoring is going to be useful to us is because we have this expression, this polynomial, that's set equal to 0. As it stands, the expression on the left is a sum. It's a sum of 3 different terms. But if we can rewrite the left-hand side or the polynomial or the quadratic in factored form and set the factors equal to 0, then that's going to let us easily solve for x. And that's all based on the zero product principle. So if a times b is equal to 0, then either a is equal to 0 or b is equal to 0, right? Because the only way we can multiply 2 factors and get 0 is that at least one of them has to be equal to 0. So let's keep that in mind, and let's look at the first couple of examples. So the first thing you want to do when you solve a quadratic equation is make sure it's in standard form. So it's set equal to 0. So if it's not, we have to move all non-zero terms to one side. Then we're going to, if possible, factor completely. Then we could use that zero product principle by setting each factor equal to 0. And then we could solve the equations that are in step 3. And then, of course, you always want to check your answers. So let's look at example 1, solved by factoring. So in A, I have x squared plus 5x plus 6 is equal to 0. So it's already in standard form set equal to 0. So now why don't we factor the polynomial? So we need 2 numbers that multiply to 6, positive 6, which is c, and add to b, which is 5. And that's going to be a positive 3 and a positive 2, right? 3 times 2 is 6. 3 plus 2 is 5. Now I have a product, right? I have x plus 3 times x plus 2. So I rewrote my polynomial as a product. And this product is equal to 0. So that tells me that either x plus 3 is equal to 0 or x plus 2 is equal to 0. And if we solve each equation on the left, I'm going to get x equals negative 3. And on the right, if I subtract 2 from both sides, I'm going to get x is equal to negative 2. So we have x equals negative 3 or x equals negative 2. Now, you always want to check your answers, right? So put your solutions into the original equation and make sure it checks out. And then I'm also going to show you how to check graphically. But why don't we let's first check the solution by plugging back into the original equation. So we have x squared plus 5x plus 6. That should equal 0. So let's go to the calculator. And first, let's check -3, and then we'll check -2. Okay, so you all should see my calculator. So let's do -3 first. So we're going to take -3. So all I'm doing is plugging it back into the original. So -3 squared plus 5 times -3, and then plus 6. So I'm just saving some time rather than doing it by hand on the whiteboard. I'm just going to plug it into the calculator, the first solution. We should get 0, and that checks out. Now let's check -2. So we're going to take -2 squared plus 5 times -2, and then plus 6. And again, we should get 0. And it checks out. I also want you to look at this from a graphical perspective. So let's just circle our answer here. So either x is equal to -3 or x is equal to -2. So I kind of want to put it all together in perspective and have you see what this function looks like as a graph and how the x equals -3 and the x equals -2 are significant. So let's go back to the calculator. Press y equals. Get rid of whatever we may have previously. And let's graph x squared plus 5x and then plus 6. And we should be in the standard 10 by 10 window. So remember, before we hit graph, we could always press zoom and option 6, which is zoom standard, and it'll bring our calculator back to a 10 by 10 window. And what's significant about this graph is, look where it crosses the x-axis. It crosses the x-axis at -2 and -3, right? If we count back to the left, -1, -2, -3, you'll see that there's two intersections, right? At -2 and -3. So that's what the solution to a quadratic represents. So when we solve for x, we're figuring out where the x-intercepts are, where the graph is going to cross the x-axis. So let's look at the next one. So for the next one, we have x squared minus 3x is equal to 4. We have to get it in standard form. We have to set it equal to 0. So I'm going to subtract 4 from both sides. So we're going to get x squared minus 3x minus 4 is equal to 0. So we got it in standard form. Now let's factor. So what two numbers multiply to -4 and add up to -3? That's what we have to think about. And it's going to be a -4 and a +1, right? Because -4 times 1 is -4, and then -4 plus 1 is -3. So now that we're in factored form, we can set each factor equal to 0 and we could solve. So we have either x minus 4 is equal to 0 or x plus 1 is equal to 0. So when I solve the one on the left, I'm going to get x is equal to 4. And when I solve the equation on the right, I'm going to get x is equal to -1. So my two solutions are either x equals 4 or x equals -1. Another way that you could write your answer is using set notation, because this isn't an interval, right? It's just two unique solutions. So we could use our set brackets and we could write -1 and and 4. That's just another way that we could write our solution. So we could either say x equals 4 or x equals -1, or we could put -1 and 4 in a set. And let's graph this and check our answer. If we're correct, the graph should go through the x-axis at -1 and 4. So we're going to graph x squared minus 3x minus 4. So we have x squared minus 3x minus 4. We want to graph it. And you'll see the parabola is going to cross the x-axis at 2 places, right? Once at -1 and then again at +4. Let's do one more just to make sure we're good. Let me just pick a different color so we kind of differentiate these a little bit. Let's do black. So 2x squared plus x equals 1. So for C, the first thing we have to do is get this quadratic in standard form. So I'm going to subtract 1 from both sides. So we're going to get 2x squared plus x minus 1 is equal to 0. Now for this factoring, we still have a trinomial, but the leading coefficient is 2. It's not 1. So we're going to have to use the AC method to factor this. So remember how we use the AC method. Take A, which is 2, and multiply it by C, which is -1. So for A times C, we're going to get -2. Now we need to think, okay, are there two numbers that multiply to B, which is 1? I'm sorry, that multiply to -2, but add to B, which is +1, right? The x term in the middle has a coefficient of 1. So what two numbers multiply to -2, but add to 1? And that's going to be a +2 and a -1, right? When you multiply them, they multiply to -2, but when you take a 2 plus a -1, we're going to get 1. So remember how we factor using the AC method? We're going to end up factoring by grouping. So we replace the middle term with the two numbers, the sum of the two numbers that we came up with earlier. So we said, okay, plus a 2x and then plus a -1x. And you don't have to write the 1. I'm just going to write it so it's easier when we go to factor. And then our last term was -1. And that's set equal to 0. So now I can divide my polynomial in half. I could factor the left, 2x squared plus 2x. I'm going to factor out a 2x, and then I'm going to be left with x plus 1. And then in my second grouping, I'm going to factor out a -1. And then I'm going to be left with my other factor of x plus 1. And now you see both expressions have an x plus 1 in common, so I could factor it out. So we're going to have x plus 1, and then my other factor is going to be 2x minus 1, and that's equal to 0. And now I could set each one of my factors equal to 0. So we're going to have either x plus 1 equals 0 or 2x minus 1 is equal to 0. Solve each one. The one on the left, we're going to get x equals -1. Or the one on the right, look, we're going to add 1 to both sides. So we're going to get 2x equals 1, and then we divide by 2. So we're going to get x equals a half. So we have x equals -1 or x equals a half. And again, we could write our solution set in set notation. So -1 comma 1/2. And let's graph this so we could see where the parabola is going to cross the x-axis. It should cross at -1 and positive a half. So graph the, well, once we set it equal to 0, right? So we have 2x squared plus x minus 1 is equal to 0. So we have y equals 2x squared plus x minus 1. Now we could graph. And you could see we have an intercept on the left at -1, and the intercept on the right is between 0 and 1, and it's halfway, so it's 1/2. So our solution set checks out graphically. We have x-intercepts at -1 and positive 1/2. So that's how we can solve a quadratic by factoring. Factor the polynomial and set each factor equal to 0, solve, and check. We have another method of solving quadratic equations, which is using the square root property. So quadratic equations in the form u squared equals d, where u is an algebraic expression and d is a non-zero real number, can be solved by using the square root property, right? Because if I want to solve for u and I have u squared equals d, if I take the square root of u squared, I'll get u, and then I just have to take the square root of d. And there's going to be two roots. So whenever we use our square root property, we have two roots, a positive and a negative root. So u squared equals d. In other words, if I take the square root of u squared, then I have to take the square root of the other side, which is d. And the square root of u squared is u. And the square root of d is plus or minus the square root of d. There's two roots, positive and a negative. That's what this is saying right here. So look, let's look at example 2. We have x squared minus 36 is equal to 0. We could factor this using the difference of squares. So that's what I meant at the beginning when I said, there are several ways sometimes to solve a quadratic. Go with the one that you're comfortable with. So I'm going to leave you with different options dependent on the polynomial. And sometimes you can use all three possibilities. Just pick one, whichever one makes the most sense to you. So I could have factored x squared minus 36 and done the difference of two squares, but the point of this is I want to practice using the square root property. So we want to get it in the form u squared equal to d, something squared equal to a constant. So if I add 36 to both sides of the equation in A, I'm going to get x squared is equal to 36. And 36 is a perfect square, right? And we want to solve for x. So if I take the square root of x squared, then I have to take the square root of 36. The square root of x squared is x. And the square root of 36 is positive and negative 6. So remember, there's two roots, because 6 squared equals 36, and negative 6 squared is going to give me 36. So I have two solutions, 6 and negative 6. Let's use the square root property again. Look at B. We have 3x squared minus 15 is equal to 0. So I'm going to use my square root property. So I'm going to solve for x squared. So I'm going to bring everything else to the other side. So we're going to get 3x squared equals 15. And remember, we want to isolate x squared so we could use our square root property. So let's divide by 3. So we're going to get x squared equals 15 divided by 3, which is 5. Now I could use my square root property, right? So if I take the square root of the left-hand side, I have to take the square root of the right-hand side. And the square root of x squared is x. And 5 is not a perfect square, right? We can't simplify it any further because there is no perfect square that goes into 5 evenly. So my answer is going to be plus and minus the square root of 5, which is 2 point something. So it's between 2 and 3 because 2 squared is 4, 3 squared is 9, 5 lives between 4 and 9, right? So it's going to be 2 point something. But let's graph this so we could see that. So let's graph 3x squared minus 15. So 3x squared minus 15, and we're expecting it to cross the graph at positive and negative square root of 5, which is like plus or minus 2 point something. And you'll see on the left, it crosses a little bit after -2 to the left of -2. So it's between 2 and 3. And then on the right, it crosses the graph also between +2 and 3. So just like we expected. So let's go to the third example. So part C, we have 5x squared plus 45 is equal to 0. Let's use the square root property again. Isolate the x squared, so I'm going to subtract 45 from both sides. So I'm going to get 5x squared equals negative 45. We want to isolate the x squared, right? We have 5x squared, so I need to divide by 5. Now I have x squared is equal to 45 divided by 5 is going to be 9, and we have negative 9. Let's use our square root property. Take the square root of x squared, the square root of negative 9. So we're going to get x equals, and this goes back to what we did in the previous section with complex numbers. So this is why complex numbers or imaginary numbers are important, right? Square root of negative 9, that's not a real number. It's imaginary, right? Because we're taking the square root of a negative. So remember how we factor that. That's going to be the square root of -1 times the square root of 9. Square root of 9 is 3. And remember, square root of -1 is equal to I. So this is going to be plus or minus 3 times I. And that would be my two solutions. They're imaginary. So let's think about what that means graphically. Because in all the other ones that we've been graphing, when we graph the quadratic, the parabola crosses the x-axis at our solution set, right? At each of those points, it's the x-intercept. But what if I have an imaginary number? It's not real, right? So I'm thinking that when I go to graph my quadratic, it's not going to cross the x-axis. There's no real places on the x-axis where the parabola is going to cross. That's what I'm thinking. So let's plot 5x squared plus 45. So this is an instance where when we go to graph, it graphed it. I didn't get an error message, right? But I don't see it. So I'm thinking the fact that we're taking a quadratic, 5x squared, we're multiplying it by 5, and then we're adding 45 to it. And remember, this graph only goes to positive 10 and negative 10 in each direction. So I'm thinking that, maybe we need to change our graph. So let's change the window so that we can see this graph better. So this is what I'm thinking. Go to the window. We have to adjust the scale, right? It's 5x squared plus 45. So I'm thinking, and you'll learn this over the next set of videos. What happens if we take one of our functions, like an x squared function or square root function or something like that, and we add something to it? It's going to shift it upwards. So I'm thinking if we have 5x squared plus 45 and it's a plus 45, maybe this graph got shifted upwards. So that affects the y max, right? But even for the x min and max, let's just go a little bit further. Like, let's go out to negative 50 and positive 50 horizontally for the x-axis. And let's make our scale 10. So this way the calculator counts in tens instead of ones. Now for the y min, let's also go out to negative 50. But for the y max, I'm going to play it safe and let's just kind of go really high. Let's go up to 500. And let's make our y scale 100. This way we count in hundreds up to 500. And now we could graph. And you'll see there's our quadratic, right? Our picture of our parabola. And look, it's above the x-axis. At no point on this graph does the parabola, right, cross the x-axis. There are no x-intercepts. And it makes sense that we got that answer, right? When we solved, we got imaginary numbers. There are no real answers. So I think it's important that, we put it in perspective, not only algebraically, but graphically as well. Another method that we have for solving quadratics is the quadratic formula. You guys are definitely familiar with the quadratic formula. Even if you don't remember it, you've seen it at some point, right? So x is equal to negative b plus or minus the square root of b squared minus 4 times a times c divided by 2 times a, where we know what a, b, and c are, right, in our standard form when we set the quadratic equal to 0. I usually use the quadratic formula if I can't factor the polynomial, the trinomial, right? Or if I can't use my square root property. So it's kind of like my last resort. Not that it's difficult, it's quicker if you could factor. But you can never go wrong when you use the quadratic formula. You can use the quadratic formula on any quadratic equation. So you can solve any quadratic equation by using your quadratic formula. It's just sometimes it's a little bit quicker to use another property like factoring or square root property. That's all. So for example 3, let's use the quadratic formula to solve these quadratics. So in A, we have x squared minus 6x plus 4. And if you try to factor, you'll see it's not factorable. So usually what I do is I like to say, okay, A is 1 in this case, right? There's a 1 in front of the x squared. B is negative 6 and C is 4. Now let's plug into our formula. So I'm going to have x equals, and I'm just following the formula that we have above, right? So x equals negative b, where b is negative 6. So I'm going to have negative 6. Be careful, right? So parentheses. Plus or minus the square root of b squared, so negative 6 squared, minus 4 times A, which is 1, times C, which is 4, and we divide the whole thing by 2 times A, which in this case is 1, right? 2 times 1. So now let's simplify. -6 is +6, so we're going to have 6 plus or minus the square root. Let's simplify what's inside, right? -6 squared is +36. Now we have 36 minus 4 times 1 times 4. 4 times 4 is 16. 36 minus 16 is 20. And we're dividing that by 2. Now we want to simplify. Simplify as much as possible. And I can rewrite the square root of 20, right? Can I rewrite the square root of 20 as the square root of 4 times the square root of 5? So remember we did this in one of the beginning videos. We were simplifying radicals by factoring, right? Square root of 4 is 2, so we're going to end up with 2 radical 5. So x is equal to 6 plus or minus 2 radical 5 divided by 2. And I see that there's a common factor, right? 2, 2, and 6 are all divisible by 2. So I'm going to divide everybody by 2. So 6 divided by 2 is 3, 2 divided by 2 is 1, and then the 2 on the bottom divided by 2 is 1. And we're going to get x is equal to 3 plus or minus the square root of 5. So my two solutions, so in the homework, if the homework wants the two solutions separately, either x is equal to 3 minus radical 5 or x is equal to 3 plus radical 5 if you had to write out the two solutions. And let's put this in perspective. 3 minus radical 5 and 3 plus radical 5. Let's go to the calculator for a minute. 3 minus radical 5 is about 0.7639. And then 3 plus radical 5 is about 5.236. So now let's graph this quadratic. So remember, it was x squared minus 6x plus 4. So we got real answers, right? So we're expecting that this graph is going to cross the x-axis at 3 minus radical 5 and 3 plus radical 5, which is about 0.76 and 5.2, right? Those are the two spots that it should cross. So let's graph. So I have x squared minus 6x and then plus 4. And I'm going to zoom back to my standard window. And you could see the intersection on the left is before 1, right? It's a little before 1, so that's about the 0.7639. And the intersection on the right is a little bit after 5, and that's your 5.236. Okay, so let's look at B. Let's practice using the quadratic formula again. A is equal to 2, B is also equal to 2, and C equals -1. So let's plug in. So we're going to have x equals negative b, so negative 2 plus or minus the square root of b squared. So that's going to be 2 squared minus 4 times a, which is 2, times c, which is negative 1. And then over 2 times a, so 2 times 2. So we're going to have x equals negative 2 plus or minus. Let's figure out what's underneath the radical, right? So 2 squared is 4. So we have 4 minus 4 times 2 times negative 1. That's going to be 4 times 2 is 8, right? 8 times negative 1 is a negative 1. But we have this subtraction here. So a negative is going to be a positive. So that's really 4 plus 8, which is going to be 12. So we have the square root of 12 and then divided by 4. Now let's reduce the radical. 12 is not a perfect square, right? But I could factor the square root of 12 as the square root of 4 times the square root of 3. And 4 is a perfect square. Square root of 4 is 2. So we're going to end up with 2 radical 3. So x is equal to negative 2 plus or minus 2 radical 3 over 4. And just like we did in the previous question, I can reduce, and it looks like everybody has a common factor of 2, right? So 2 goes into itself once and into 4 twice. So my simplified answer is going to be x is equal to negative 1 plus or minus 1 radical 3, or just radical 3, divided by 2. And if I want to write it as two separate answers, either x is equal to negative 1 minus the square root of 3 over 2, or x is equal to negative 1 plus the square root of 3 over 2. So those would be my two solutions. And let's do one more. So let's look at C. We're using the quadratic formula again. So we're going to have A is equal to 3. B is equal to negative 2. And C is equal to 4. So x is equal to negative b, so negative 2, plus or minus the square root of b squared, so negative 2 squared, minus 4 times a, which is 3, times c, which is 4. And we're going to divide that by 2 times a, so 2 times 3. And let's simplify. So we're going to get x equals a negative 2 is a positive 2, right? Plus or minus. Now, let's simplify what's underneath the radical. So negative 2 squared is 4. And then we're subtracting a 4 times 3 times 4. So that's going to be 4 minus 48, which is going to be a negative 44, and then over 6. As soon as we see that negative underneath the radical, what thoughts are going through our head, right? Imaginary. Our answer is not going to be real, right? We're going to have to write this in terms of I. So let's think about how we can rewrite the square root of negative 44, right? So square root of negative 44, I could factor that as the square root of negative 1 times the square root of 4 times the square root of 11, right? 4 is a perfect square, and 4 times 11 is 44. So we're going to end up with square root of 4 is 2. Square root of -1 is I, right? And then we have the square root of 11. So 2 times I times the square root of 11. So x is equal to 2 plus or minus 2 times I times the square root of 11 over 6. And then it looks like all three expressions have a common factor of 2, right? 2 goes into itself once, into 6 3 times. So x is equal to 1 plus or minus I times radical 11 over 3. And if I want to write it separately, x is equal to 1 minus I radical 11 over 3, or x is equal to 1 plus I radical 11 over 3. So that's how we use the quadratic formula to solve a quadratic equation. And like I said earlier, I would use this approach if I'm having a hard time factoring the polynomial, or maybe it is factorable, but the numbers are too large, and I'd rather just plug into the quadratic formula. It's going to be quicker. So to wrap things up, let's just go over the discriminant and then we'll do 2 application questions. So the discriminant is just the expression underneath the radical, the b squared minus 4 times a times c. I want you to realize something. When the discriminant is positive, greater than 0, there's going to be 2 unequal real solutions. So that was like up here in example A and B. My radicand, right underneath the radical, my discriminant simplified on the left hand side here to 20, right? I have the square root of 20. And then in B, we ended up getting the square root of 12, right? Both of those are positive. They're greater than 0. And I got 2 different answers, right? Then part C was this third case. If the discriminant's negative, there's going to be 2 imaginary solutions, right? So when we solved here, my discriminant was negative 44, hence I got the 2 imaginary answers. And if we were to use the quadratic formula and underneath the radical, our discriminant was equal to 0, then there's one real repeated solution. So the discriminant can tell us just by looking at it, the number and type of solutions that we're going to have. So just, to have that in the back of your mind. So let's wrap up by doing 2 application questions. So 2 word problems. So example 4 and 5, and then we'll wrap it up. So example 4 says the formula P equals 0.01a squared plus 0.05a plus 107 models a woman's normal systolic blood pressure P at age A. So her blood pressure depends on her age, right? Use this formula to find the age to the nearest year of a woman whose normal systolic blood pressure is 115 mmHg. So we're being given a value of P, right? If her systolic blood pressure P is equal to 115, then the question is, what is A? So we're trying to solve for A, right? Which is age. So age is A, and we're being asked to find the age of a woman whose normal systolic blood pressure is 115. So I'm going to set P, so we know that P is equal to 0.01a squared plus 0.05 times a plus 107. But we're being told that P is equal to 115. So I'm going to replace P in the equation with 115. So that's going to equal 0.01a squared plus 0.05 times a plus 107. And this equation right here that I'm going to highlight in green for P, that's a quadratic, right? It follows the form ax squared plus bx plus c. So this is a quadratic. How do we solve it? Well, we just did a whole bunch, right? First of all, set it equal to 0. So I'm going to subtract 115 from both sides. So we're going to get 0 equals 0.01a squared plus 0.05a. And then 107 minus 115 is going to be minus 8. Now, this one to me, I'm looking at it and A is 0.01, B is 0.05, and C is -8, right? From my standard form, ax squared plus bx plus c. I'm not about to try to factor that, right? Thinking about, all right, AC method, too much. These numbers, one's a decimal, one's a whole number. So in a case like this, where it's going to look tedious to even try factoring it, if it even is factorable, I would just use your quadratic formula. So remember, x is equal to -b plus or minus the square root of b squared minus 4 times a times c divided by 2a. So in this case, A is equal to 0.01, B is equal to 0.05, and C is equal to -8. So let's plug in now and solve for A. So A is going to be equal to -b, so -0.05, plus or minus the square root of b squared minus 4 times A times C, which is -8. And then divide that by 2 times A. So 2 times 0.01. So we're going to have -0.05 plus or minus the square root. This I would just plug into the calculator, right? So 0.05, plug in what's underneath the radical. 0.05 squared minus 4 times 0.01, and then times a -8. And we're going to get 0.3225 underneath the radical. And then 2 times 0.01 is 0.02. So divided by 0.02. So let's continue down here. So the square root, take the square root of 0.3225. If we go 4 places, it's about 0.5679. So A is equal to -0.05 plus or minus 0.5679 divided by 0.02. So either A is equal to -0.05 minus 0.5679 divided by 0.02, or A is equal to -0.05 plus 0.5679 divided by 0.02. So let's calculate the one on the left. So let's calculate -0.05 minus 0.5679 divided by 0.02. So for A over here, I'm getting -30.895, or A is equal to, now let's do -0.05 plus 0.5679 divided by 0.02. And I'm getting A is equal to 25.895. So we have two answers, right? But in a word problem, we have to look and say, okay, in the context of the question, which answer makes sense here? You can't, we're looking for age, right? What's the age of a woman whose blood pressure is 115? You can't be negative 30 point something years old, right? So we have to reject the answer that doesn't make sense. It does make sense to be about 26 years old, right? And I said, find the age to the nearest year. So to the nearest year, her age is going to be about 26 years old. And that would be my solution. So a 26-year-old, based on this formula, is going to have a systolic blood pressure at age 26 of about 115. So you want to make sure that your answers are reasonable. Obviously, you can't be negative 30 years old, so we would have to reject that possible solution. And let's do one more. There's one more word problem. So for this one, it says the alligator, at one time an endangered species, was the subject of a protection program. The formula P equals negative 10x squared plus 475x plus 3,500 models the alligator population P after X years of the protection program, where X, so we have a restriction on the domain here. X could be between 0 and 12 years. I guess that's how long, the protection program existed. So how long did it take the population to reach 5,990 alligators? So here's my formula to model the alligator population, where P is the population amount and X represents the number of years of the protection program. So the question is, how long did it take the population to reach 5,990 alligators? So X is years, right? So we're looking for a value of X when the population P is equal to 5,990 alligators. So if my formula is P is equal to negative 10x squared plus 475x plus 3,500, I can replace P with 5,990, right? Because I want to know when the population is going to reach that amount. So I replace P with 5,990, and now the only unknown in this equation is X, and that's the time it took the population to get to 5,990. So we need to solve for X. We have a quadratic, right? This is a quadratic equation. It's in the form ax squared plus bx plus c. Let's just set it equal to 0. So I'm going to subtract 5,990 from both sides of the equation, right? Set it equal to 0. So I'm going to get 0 equals negative 10x squared plus 475x. And let's do 3,500 minus 5,990. And we're going to get minus 2,490. Now we're ready to plug into the quadratic formula, right? And we know that x equals negative b plus or minus the square root of b squared minus 4 times a times c over 2a. So here we have a is equal to negative 10, b is equal to 475, and c is equal to negative 2,490. So x is going to be equal to negative b, or negative 475, plus or minus the square root of b squared minus 4 times a, which is negative 10, times c, which is negative 2490. And we have to divide that by 2 times negative 10. So let's simplify what's underneath the radical. So put in the calculator 475 squared minus 4 times negative 10 times negative 2490. So I'm getting negative 475 plus or minus the square root of 126,025. And then divided by 2 times negative 10 is negative 20. Take the square root of 126,025. We're going to get 355. So this is equal to negative 475 plus or minus 355 over negative 20. So either x equals negative 475 minus 355 over negative 20, or x equals negative 475 plus 355 over negative 20. So let's plug each of those into the calculator. The one on the left, take negative 475, subtract 355, and then divide by negative 20. So I get 41.5. Or now do negative 475 plus 355. Now divide that by negative 20. And I get 6. So we have two potential answers here. We got 41.5, and we're in years, right? Because X represents years, or 6 years being in this protection program. So how do I know which one is the correct answer? Well, if we go back to the problem, you see how here it says that X has to be between 0 and 12. So that means that we can reject the answer of 41.5 years because that falls outside that domain, right? X could only be between 0 and 12, and 6 falls within 0 to 12, right? So my solution is going to be X equals 6 years. So after 6 years of the protection program, the population was 5,990 alligators. And this wraps up section 1.5, and in the next lecture, we will start section 1.6.